Alright everyone, let's go through a problem that is near and dear to all of our hearts at this point, and that is the wire problem. So the problem states, with 4 feet of wire, you are to create a circle and a square and enclose as much area as possible. Otherwise, maximize the area. Okay, so I've sort of sketched what we have right here. So we're going to have a circle with some radius r and a square with some side length x. So now let's talk about our constraint and our target equations. So our constraint equation, well, that's going to have to deal with what we only get. Well, we only get 4 feet of wire. So we're going to say that our perimeters, because that's what the wire is going to be, it's going to be around them, are going to be 4 feet total. So 4 feet of wire is equal to, well, the perimeter of a square is 4 times the side length plus 2 pi times the radius. Okay, so this is our constraint. Now let's talk about our target equation. So if we're talking about a target equation, it's going to be whatever we're targeting. And in this case, we're targeting the area. So let's say our total area, which we will refer to from now on as A, is going to be equal to, well, the area of the square, so x squared, plus the area of this circle, so pi r squared. Okay. So we have our constraint, we have our target, and now we would like to make our constraint function give us our total area function in terms of one variable. So what I mean by that is we're going to take our constraint function and I'm just going to rearrange it. And I'm going to say r is equal to 4 minus 4x, all that divided by 2 pi, which is the same as 2 minus 2x over pi. And then we're going to use this and we're going to substitute for our r in our area equation, which is our target. So a is now equal to x squared plus, and now we're going to have pi times, and we'll replace our r, 2 minus 2x over pi squared. Excellent. So I am going to skip a little bit of the algebra because I feel this is something you guys can work out. And I'm going to say a is equal to, and then finally we'll have x squared plus 1 over pi times 4 minus 8x plus 4x squared. All right, so this is our area. And now we want to find our critical points. So find critical points. So how do we do that? We look at our area function, we look at the rate of change of our area function, or a prime, which is also dA, and in this case we're taking the derivative with respect to x, dA dx. Okay, and so dA dx is going to be, well, you can take this derivative here pretty easily, 2x, and I'm going to simplify a bit as well, 2x plus 8 over pi x minus 8 over pi. And we want to set this equal to 0. So setting this function equal to 0 finds our critical points, which is what we're doing. We're finding our critical points. So let's say 0 equals 2x plus 8 over pi x minus 8 over pi. Well, at the same time here, we can solve for x. Again, I'm going to skip some steps. Pause the video and try it yourself if you'd like to see these steps. But so I have 8 over pi divided by 2 plus 8 over pi, which is approximately equal to 0.5601. On the AP, you're going to be rounding to 3 decimal places, which we haven't explained yet, but I'll talk about that someday in the future. So now we have to figure out, is 0.5601 a min or a max? And so for this, I'm going to go to my calculator, which I have already gone into, and I'm going to go to y equals, and you can see that I have our function here set up right here, as well as the derivative, which is what we're working with right now. So I'm going to go ahead and make the function that is shown on our calculator the derivative, and I'm going to go to the table. And so you can see that I rounded here, and it gives me something close to 0, but not exactly. And then I'm trying a value a little bit above, and I'm trying a value a little bit below. So a little bit above our critical point, we get 2, which is positive, and a little bit below, we get a negative. So if we want to look at this visually, we can see that a little bit above, so I did the value 1, and I got a positive f prime. So this is our f prime, this is our x, and this is what it looks like, so a positive slope. At the 0.5601, I got a 0 slope, and then a little bit below at 0, I got that -2 or something, -2-ish. This was +2-ish, and we get that. So we have a minimum, right? Well, but wait. We wanted a maximum area right here. And this is a minimum. So we have not completed what we want. So we actually want to find the maximum area. And how we're going to do this is by also looking at that caveat that we had with critical points. So if you remember, we had find and check the critical points, but then we had that little thing that said also look at endpoints. So let's think about our endpoints. Well, our endpoints, so to speak, on this problem are going to be either when the circle has all the wire or when the square has all the wire. So if the circle has all the wire, then the square is equal to 0. Or if the square has all the wire, then the circle is equal to 0. So let's see how that would affect our constraint equation here. It would say, well, excuse me, not our constraint equation, our target equation here. It would say, well, either our circle has 0 area, in which case our total area is equal to x squared, or our square would have 0 area, in which case our area total would be equal to pi r squared. So let's try each. So let's say if x equals 0 and if r equals 0. So if x equals 0, looking back at the constraint equation, we have 4 equals 2 pi r, or more simply, then r equals 4 over 2 pi, correct? And if r equals 0, then we have x equals 1, because it would be 4 equals 4x. Well, let's look at this. Which one of these maximizes the area? So again, if x equals 0, we talked about this already, it would give us the total area equation of pi r squared. And if r equals 0, so this would be pi r squared would be our total area. And if r equals 0, then just x squared would be our total area. So let's look at these. Well, 1 squared, well, that just gives us 1. pi times 4 over 2 pi squared, well, that would give us 4 squared divided by 4, so 4 again. And then divided by pi squared times pi would be over pi. So now we have these 2 points to consider, 4 over pi and 1. And really, 4 over pi is very similar to 3. Or 4 over pi is very similar to 4 over 3. And we can say this without a doubt. And so this would be our maximum. And if we want to, we can look at our graph here of our function now. So just looking at our function graph, we can see that this is the case. So our function graph looks like this, but our x constraints are going to be 0 to 1. And here, it should be clear, or somewhat clear based on the resolution of the graph, that the highest point occurs right about here. All right, thank you guys for watching.